Hi everybody, it's time to get started with video 1 of lecture module 5, where we are going to discuss the origins and evolution of the moon. How did the moon come to be, and how did it end up in its present state where we have the cratered highlands and the lunar maria dominating the surface of the moon? This is a rather fun section where we're going to actually approach this from a scientific standpoint, where we are going to look at a body of evidence, and then we're going to come up with go through all the historic hypotheses of how we can form a moon and see whether or not each hypothesis supports the evidence. So this is a good scientific detective story and just a very interesting one in general. One of the key points of evidence is understanding the interior structure of the moon. That's going to help us understand its formation, which is going to be our launching point, and we'll discuss all the evidence that we are going to have in our tool belt that we need to compare our formation theories or hypotheses against. We'll go through the current and 3 historic formation hypotheses, and we will see which one best matches the evidence. The one that best matches the evidence is the one that we currently accept as the formation of the moon scenario. And finally, we're going to end with, once we form the moon, how do we get the moon as it is today? How do we get the lunar maria, and how do we get the cratered highlands? So we need to talk about how the moon evolved to its present state. And that should wrap out Unit 2, Part 4, and that will leave us on our tour of the terrestrial planets for the remainder of the semester. So jumping right in, one of the most important things in the story of understanding how the moon formed is understanding the interior structure of the moon. And out of all the celestial bodies we're going to talk about, we know Earth's interior structure the best, since we use earthquakes, and we have earthquakes always occurring here on Earth. So we have a very, very detailed analysis on Earth's interior. Out of all the bodies, we know the moon's interior the second best. Why? Because the astronauts brought seismometers with them up to the moon, so that when they went to the moon, they plunked seismometers on the surface. So there are several seismic stations stationed around the moon, and the moon does have moonquakes. They're not created by plate tectonics, which is the reason that Earth has so many earthquakes, but there are things like asteroid impacts that are creating new impact craters. There's cliffs that will slump and fall down. There are slight tectonic activities still happening on the moon as well. Each one of these creating a moonquake, which then will send out these seismic S waves and P waves, coursing throughout the interior of the moon, where they can be detected by all the seismic stations left behind by the astronauts, and we can play the same game that we did with the Earth to start determining the interior structure of the moon, not only the density structure, but the size of the crust, the size of the mantle, and information about the core. Surprisingly, the moon being such a small baked potato, we're a little bit surprised that it still does have a small, partially molten outer core. A small core overall, and a very, very small, partially molten outer core. Not fully molten like Earth, partially molten. So we have an S-wave shadow, which tells us that it does have a little bit of a molten part of its core. And we have a P-wave shadow, which indicates that we have an iron core, and it gives us the size of the iron core. What does that all help us determine? Well, this is the interior structure of the moon as we know it today. So from center to the surface, the moon has a radius of 1,738. So we'll start from the center, moving outward. The core structure, so the core of the moon, extends to 20% of the way to the surface. So it's 20% of the moon's radius. If you remember when we talked about the size of Earth's core, excuse me one moment. If you remember when we talked about the size of the Earth's core extends from the center up to 55% of the radius. So one of our key observations is, yes, the moon does have an iron core, but it is significantly smaller than what we expect. The moon is deficient in iron. It lacks the same amount of iron relative to the size of the planet that the Earth does. Something has to have happened that makes it so the moon has a relatively low total amount of iron in it. Then we get into the mantle, which extends nearly all the way up to the surface. And the mantle is strikingly similar to Earth's mantle in composition. So it's primarily high-density rocks made out of olivine and pyroxene. You don't have to remember those two minerals. They're the two most abundant minerals in the solar system. So I figured I'd go ahead and give you that detail just in case we have any geology people out there that get excited by seeing those two words right there, olivine and pyroxene. And finally, we have the lunar crust. and the crust is relatively thicker than Earth's crust. The lunar crust is about 3% of the moon's radius, making it a pretty thick crust. And for our geology people out there, it's a northocite, is mostly what the crust is made out of, which is the kind of rock that you expect if you have a lava. And then as the lava cools, the first stuff that would turn into a solid would be the lightest, least dense stuff that would float to the top, and that would be a northacitic materia. So if you do a comparison between the size of the moon's crust is 3% of the radius, Earth's crust by comparison is 0.6% of the radius. So whatever formed the lunar crust is a fundamentally different process than what formed Earth's crust. And we also have noticed that there's an oddity that might be reflective of this near side, far side dichotomy. So the near side, the side of the moon that points towards the Earth, has a thinner crust than the far side crust. So the near side crust is about 30 kilometers thick. The far side crust is about 60 kilometers thick. So about twice as thick. So let's start putting all this information together and start building all the evidence that we need to bring to bear about how our moon formed. So we're going to bring we're going to divide the evidence into three primary categories: the composition of the moon, so what is it made out of, the physical considerations, can we form the moon in that manner, can we look at the physics of it, and will the physics work? Can we actually build a moon with physics and have everything work out? And then we also have to have an age consideration. And we'll start with the age consideration, a little bit of the details. So the moon is younger than the Earth. So this tells us that the moon formed after the Earth did. It's not younger by a whole lot, maybe about 100 million years or so, but it is younger than the Earth. So we need to form the Earth first, and then we're going to form the moon. So let's now look at the two meteor parts. Let's talk about the composition of the Earth versus the moon. So what we saw with the mantle of the moon is that the rock composition, what the rocks are made out of, is remarkably similar to Earth's mantle. So the overall rock composition of the Earth and the moon are strikingly similar. Something must have happened so they have the same kind of rocks making it up with a remarkably similar chemical composition. We're also going to have to leverage the fact that something had to have happened to left the moon having a smaller iron core than is expected. Just by condensation theory, if the moon formed on its own, as its own little planetesimal or protoplanet, then it should have about the same size iron core as the Earth does, but it has a much smaller core. This is reflected in the density of the moon as well. The density of the moon is 3,300 kilograms per cubic meter, while the density of the Earth on average is 5,500 kilograms per cubic meter. If the rocks are the same composition, the only difference there can really be the iron, the size of the core, which would have to be a lot smaller to bring down the density of the moon. There's a lot of finer detail that goes into this story of how the moon formed. So I've dropped a few scientific articles that you can go read from the journal Science that deals with the finer details of this story, things that we've discussed before, like oxygen isotopes, but also volatile contents, things like that. There are a lot of finer details that really make this one of the more interesting stories in planetary science. So what are our physical considerations that we have to go on to? And really this comes down to, given a formation hypothesis, is the physics going to work? So let's think about the size of the moon relative to the Earth. The moon is extraordinarily large compared to the object that it orbits. So relative to the object that it orbits, the moon is the largest natural satellite of all the planets. It's not physically the largest, but it's 27% the size of the planet that it orbits. No other moon in the solar system can boast a number so high, which means that we really need to consider the physics of things. And really, we're going to go back to angular momentum, that momentum of rotating objects. So we can measure what the current angular momentum of the Earth-Moon system is. Since we know angular momentum is conserved, we know that any formation scenario must produce that amount of angular momentum. So we need to actually consider the formation scenario and whether or not all the physics, all the angular momentum, all the rotational physics, all the gravitational physics is going to work out. So given how big the moon is, we have to consider whether or not the moon could end up where it is in the orbit that it is. If it can't, then our hypothesis on how the moon formed would be a bad one. And once again, just keep in mind that the moon is younger. So let's dive in. We're going to go through the historical ones, and we will end with the correct, or I should say, the currently accepted hypothesis of how the moon formed. So, the origin of the moon. One of the first ideas is one of the most natural ideas. It's called the co-formation hypothesis, sometimes called the sister hypothesis. And what I'm going to do is we're going to discuss what each of these hypotheses are, and then we're going to highlight whether or not the hypothesis supports the evidence that we have or does not support the evidence that we have. If it supports it, I'm going to highlight that bullet point in green. If it doesn't, I'm going to highlight it in red. So the co-formation hypothesis. The Earth and the moon form at the same time out of the same disk material. So they both form as their independent protoplanets, but they form in place with the moon in orbit around the Earth. So what does this mean? If they formed at the same time in the same place, then this explains the remarkable similarity between the rock composition. If they formed at the same place in the solar nebula, there'd be the same building blocks available. Therefore, you should have the same rocky composition. So good, we have a check mark for the rock composition. Physics, no real argument against this. We see binary systems throughout the universe in a lot of different contexts. So not a really big argument against this. You could form these things in a co-formation scenario. However, the amount of iron, if these two objects formed out of the same material in the solar nebula at the same place at the same time, they should have the same relative amount of iron. So the moon should not be deficient in iron. We observe the moon to have a very small iron core compared to what we expect. So this one cannot explain that. This one should give the moon a much larger iron core. So the co-formation hypothesis cannot explain the size of the moon's iron core. Also, if they're forming at the same time in the same place, they'd have the same age. So we can support two of the considerations, but we have a failure on two others. So I'm going to give this theory overall. Does it actually explain the evidence? Can it give us the moon that we currently see? It's a big old nope from me. So we do not accept this as our current formation of the moon idea, and it's not even really talked about as a serious consideration anymore. All right, another idea. If that one didn't work out, let's put back on our thinking caps and think about something else. All right, we got to get a smaller iron core. Okay, but we want a smaller iron core. I got it. Okay, so we have the solar nebula. Let's form the Earth in one location. That gives it the relative amount of iron to rock that it has. And let's form the moon somewhere else, maybe out more towards Mars, where you might expect there'd be a lower amount of iron to rock. So maybe that will give us a iron deficient thing. So we can form the moon in one place in the solar nebula, form Mars in another place, or the moon in another place in the solar nebula. And then during all the stuff on all the protoplanets and planetesimals are moving around, perhaps the Earth gravitationally captured the moon and brought it into orbit. We call this the capture hypothesis. The Earth and the moon formed separately at different locations in the nebular disk, the solar nebula, and then the moon was captured by the Earth. All right, let's take a look at the evidence. Could we have a younger moon? Yeah, the moon could be younger. We could form the Earth first, and then out here, form the moon a little bit later, giving us the different ages that we see. So that one would work. Amount of iron. Yeah, that was the entire reason I came up with this idea, that we use the fact that it formed somewhere else in the solar nebula that maybe had a different ratio of rock to iron to explain the relative lack of iron in the moon. Composition, though. So if we're using a different part of the nebula to get a different amount of iron to rock, we would also expect a different chemistry for the rocks. The rocks would have a different balance of what minerals are there. So this one would not give the moon to have a mantle and crust material, the rocky composition, to be strikingly similar to Earth's mantle and crust. So they can't explain that. That is a huge flaw. In physics, can the Earth, does it have enough gravity to capture something that's 27% its size? You can run scenario after scenario, computer model after computer model, work the math any way that you want it. It's essentially impossible to capture a moon of our size and have the orbits work out as they are, have the total angular momentum be what it is today. There are a few extraordinary scenarios, but you're talking about like one in multi-billion shots. So this one, I'm also going to give a big note to. Okay, put on our thinking caps again. All right, we need a smaller iron core, and we need the same mantle rock composition on the Earth and the Moon. What can we do? What can we do? Got an idea. Okay, so we have our proto-Earth. It's young, it's the radioactive materials, it's mostly molten. So here we have basically this big ball of lava in outer space. It's differentiated, it's sunk the iron to its core, or it's in the process of sinking its iron to its core. And then we have all the rocky stuff on the towards the surface. All right, so now let's get this thing rotating really, 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 really fast. Let's rotate the Earth incredibly fast. So I could go ahead and rotate something really, really fast, like this golf ball. And if this golf ball was coated in water, or I put a thin packing of sand on the outside and I threw it in the air and spun it, what would happen? It would sling off that material. So if you can get the Earth, early Earth, rotating fast enough, so fast that the surface would be at or near the escape or beyond the escape velocity of the early Earth, you can literally split the Earth. You can fission off, you will throw off a small little chunk that'll balance out the angular momentum so that everything works out. This is called a rotational fission event. We see these with asteroids. Things get spinning too fast, faster than, so the rotational physics, the forces involved are stronger than the gravity holding it together. You'll splat out, you will fission off a piece. So this brings us to the fission hypothesis. The Earth and Moon formed as a single object, and due to a very high rotation rate for the early Earth, the Earth spun off a moon. And this is what we call a rotational fission event. And then what got spun off would already be in orbit, and that would become the moon. Composition, yes. This idea came up to explain the similar rock composition between Earth's mantle and the moon's mantle. If we differentiated the Earth, what material is going to get spun off? The outer material. So you're going to end up with the same sort of rocks in the Earth's mantle as you do in the moon's mantle. Good work. All right, thank you, fission hypothesis. Amount of iron. Well, you had already put most of the iron in the core of the early Earth before you spun off rotationally fissioned the moon. So you'd expect the moon to be deficient in iron. We got the composition. Finally, we have an idea that gets both the composition, both the rock composition and the lack of iron that the moon has. Oh, and we formed the Earth first, and then we spun off the moon. The moon would be younger. Ooh, 3 out of 4. All right, physics. Do you work in this one? Sadly, no. What reason is there to get the Earth spinning so fast that it could have a rotational fission event? There aren't really any physical processes that could do that could get the Earth spinning so fast that it would experience a rotational fission event. So that's just not expected. And even if the early Earth could spin fast enough for a rotational fission event, you can run through the math of it, the physics of it. That spun off object would not have a stable orbit, so it would not be in an orbit around us. It would not be a moon. It would have become its own little protoplanet and whoop, went off into the solar system to do whatever it's going to do, play its game of Highlander or lose the game of Highlander. So the physics on this one doesn't work. So currently, we give this one a nope as well. All right. Man, it seems almost impossible, right? How can we get a moon? And this idea sounds wild. But remember, there was a lot of interaction between the protoplanets and planetesimals early in the formation of the solar system. So let's come up with what sounds like a ridiculous idea. It's called the giant impact hypothesis. So we have the young, molten, still mostly molten Earth. It's differentiated. Now, we have the proto-Earth. Let's consider another protoplanet about the size of Mars. Let's call it Theia, because this is going to end up being a good idea, and so good that we end up giving this hypothetical protoplanet a name. So we have a Mars-sized protoplanet called Theia, and early after Earth's formation and Theia's formation, they collided in a giant impact. in a glancing blow. So we have the Earth, here we have Theia, and it came in and hit at a low angle. This sort of impact would be very, very energetic. It caused lots of destruction, form a debris cloud around the Earth, and then out of that debris cloud, we could put together the moon. And that is the giant impact hypothesis. We had a giant impact that basically blasted a whole bunch of material off of the Earth, and then all that material formed a ring around the Earth that coalesced and formed the moon. Sounds ridiculous, right? Well, let's look at what it would explain. So, Theia's iron core, and you can run simulation after simulation. I have a few of these in the supplemental slides so you can see what's going on. So Theia's iron core and the simulations would mostly end up in the Earth. The debris cloud that forms around it would be made out of a pretty much equal mixture of rocky Earth stuff, rocky Theia stuff. So the two objects that form, the mantle, the rocks, are now going to have the same composition. So we can get the composition to work as well. This is having the moon form after the Earth. We had the collision of the protoplanets that then led to the formation of a third object, the moon. And then the Earth and Theia kind of combined, and some of the material of Theia went into the Earth, some went into the moon. And believe it or not, the physics works out. This can really happen. It's not that hard to build physics into a computer model that can form a variety of moons this way. So the physics actually works out as well. This one can explain all of the evidence, and we know that giant impacts were common in the early solar system. So it's not like this is even a wild expectation where we have to specially arrange things to have a protoplanet run into Mars. So this is our winner. This is our current accepted idea of how the moon formed. And I just want to go ahead and put this up here. This is for your review. This is just going through and explaining what I just said. That shows us that it supports all of the evidence. So yes, we have our idea of how the moon formed. And I did want you to show you not a video. I have links to a video right here, but this is just a snapshot. So we're watching time progress. So time 1, 2, 3, 4, 5, 6. Notice that it zooms out down here. So this is zoomed in and then it zooms out so we can see the situation from further away. This is done by a researcher, Robin Canup, at the Southwestern Research Institute. She does amazing modeling of not only moon formation, but of all sorts of other things as well, like the rings of Saturn. And here you have Theia. The red is iron, the blue is silicates. They're going to collide in a glancing blow, and all it's going to do is let physics do its thing. As these things sort of combine together, you can see how everything's going to work out. So now you can see you're forming this debris cloud around it, around the protoplanet. You can see that the iron is going to settle mostly towards the center, and then you're going to have a debris cloud that's mostly made out of the silicate rocks, and that debris cloud can quickly form the moon. So I encourage you to check out those videos. I guess I took it out of the supplemental slides, and I put it right here. So this is one of the simulations. This is an older one. But you can see what's going on and how to form it. Now the temperatures, this is a temperature scale. So you're looking at the temperatures of the materials. So we still have the evolution of the moon, but this has already been a pretty long video. I'm going to split off and have 5 videos for this lecture module instead of 4. And I'm going to have a short one about the evolution of the moon as its own video. I will see you in that bonus video, which will now be video 2. Thank you for tuning in, and I hope you enjoyed our story of how the moon formed.